Welcome to the Chem is Try channel. This channel is aimed at looking at ordinary level as well as advanced level chemistry. These are the areas we want to look at in this channel. We're going to have lectures, we are also going to have some experiments, we're also going to look at practical activities, design questions, and cover some past exam papers. That's the main objectives of this channel. So today we are going to look at our first topic. We are going to look at electrochemistry, and this topic is going to cover, is relevant for both ordinary as well as advanced level, SIMSEC as well as Cambridge syllabuses. So we are going to look at electrochemistry. We are going to begin with the redox reactions. By the end of this lecture, we should be able to define oxidation and reduction. We should be able to define oxidation and reduction, and we should be able to define these terms. One, in terms of oxygen. Two, hydrogen. Three, in terms of electrons, as well as 4 in terms of oxidation number. You should also be able to define what the term oxidation number also means, and also calculate. Should also be able to calculate the oxidation number of an element, in a compound. So that's what we want to be able to achieve this tutorial. So let's begin. Let's start by defining oxidation. So oxidation, in terms of oxygen, it is addition of oxygen. And in your daily lives, in our daily lives, we are experiencing a lot of these oxidative reactions. For example, when you burn a fuel, okay, let's take ethanol, for example, or your methane gas for heating. You react with oxygen to form. We have added oxygen to carbon. So in this particular case, carbon has been oxidized. Why? Because oxygen has been added to the carbon. In the reactants, there is no oxygen, but in the products there is now oxygen. As a result, we can say the carbon in methane has been oxidized. Why? Simply because oxygen has been added to it. And we can see that oxygen has been added to it by looking at the product formed. The product now has carbon associated with oxygen. Okay, so the combustion reactions which take place, they are all oxidation reactions. In our body, I'm able to speak so energetically. Why? Because I've been fueled up. The fuel that we get it from the reaction, the respiration reaction, where glucose reacts with oxygen. Again, we are adding oxygen. So that is oxidation. when rusting occurs, we are adding oxygen to the metals, so that at the end we have rusting. There are so many different examples that we can consider under oxidation in terms of addition of oxygen. So this is one of them. So reduction in terms of oxygen, still in terms of oxygen, then reduction is now the removal of oxygen. It is the opposite of oxidation. So let's do this. Let's look at the extraction of metals, which are, when you look at the reactivity series, they are not very reactive. They are not at the top and neither are they at the bottom. They are in the middle of the reactivity series. Examples like iron oxide. We can obtain iron from the oxide by reacting with carbon monoxide, and that is the reaction. Here the iron is combined with oxygen. It has been oxidized to form the iron oxide. But when you now want to get the iron back, we must remove the oxygen. And we remove the oxygen by reacting with carbon monoxide. So in this case, iron oxide, the iron in iron oxide is reduced. Why? Because oxygen has been removed from it. But what has happened to the carbon in carbon monoxide? The carbon in carbon monoxide is now oxidized. Why? Because oxygen has been added to it. Here there is only one oxygen, but let's go to the products. We now have two oxygens. So oxygen has been added. Look at the definition above. Addition is oxidation. So carbon monoxide is oxidized, whereas iron 3 oxide is reduced. So from here to there, this is reduction. And from here to there, this is oxidation. So when oxidation occurs, reduction also occurs. So these processes, they normally occur at the same time. So this is an example. These two are examples of redox. These are redox reactions. Redox. So this is a redox reaction. So what can we say a redox reaction is? A redox reaction is basically a reaction where oxidation and reduction occur at the same time within the same reaction. Oxidation and reduction are taking place simultaneously. That is what a redox reaction is, and we can see as demonstrated in that reaction, which is showing the reduction of iron 3 oxide in order to obtain iron, the metal iron. Okay, let's move on. Let's define oxidation, reduction in terms of hydrogen. So in terms of hydrogen, oxidation is removal of hydrogen, and reduction is addition of hydrogen. Let's look at this example. Consider this example. Hydrogen sulfide plus chlorine gas, so that we produce sulfur plus HCl. Two of them is now balanced. What is happening here? Sulfur has been oxidized. Why? Because hydrogen has been removed from it. Here in the reactant side, we have sulfur connected to hydrogen. But in the products, the sulfur is no longer connected to hydrogen, which means hydrogen is being removed from it. Therefore, the sulfur in hydrogen sulfide is undergone oxidation. Whereas the chlorine, in the reactants, the chlorine is on its own, but in the products, it is now connected to hydrogen, which means hydrogen has been added to it. Hence, chlorine has been reduced. So, again, this is oxidation and this is reduction for the reasons given. Hydrogen has been added to chlorine. You can see the hydrogen here. It has been added. And here this is oxidation. The hydrogen here has been removed from the sulfur so that it will now get the sulfur on its own. So this is an oxidation reaction because hydrogen is being removed from the sulfur. Oxidation. Then let's move on. Let's look at those terms in terms of electrons. In terms of electrons, oxidation is loss of electrons. Let's look at the metals. Group 1, group 2, group 3 elements. The reason why the atoms of the different elements are involved in bonding is because they want to attain a noble gas configuration, and they can achieve this objective either by gaining electrons or losing electrons or sharing. So the metals, they find it much easier to lose the electrons in the outer shell because in terms of energy, they will use less energy to lose 1, 2, or 3 electrons, which will be in the outer shell, rather than gaining 7, 6, or 5 electrons. So it will be easier for them to lose the electrons in the outer shell in order to attain the noble gas configuration. So let's consider sodium, for example. It's an element in group 1, 11 protons, so 2, 8, 1. So the outer shell only has 1 electron. So sodium will find it much easier to lose 1 electron in order to attain a noble gas configuration. But in so doing, it is losing an electron. Thereby, it is undergoing an oxidation reaction. Whereas on the other end, the non-metal end, from group 5, 6, and 7, the elements, they now have 5 electrons in the outer shell, 6 or 7 electrons. They will find it much easier to gain 3, 2, or 1 electron in order to attain the noble gas configuration. So these ones, they find it easier to gain. So reduction is gain of electrons. How many they gain depends on the position, their positions in the periodic table. So let's take, for example, oxygen, which is in group 6. So because it's in group 6, it means it has 6 electrons in the outer shell, so it will be easier for it to gain 2 electrons in order to gain a noble gas configuration. This is the oxygen atom. So when I'm now reacting oxygen and sodium, let's note oxygen exists as a diatomic molecule. In its uncombined state, it is a diatomic. So let's now look at the reaction which is taking place. What I've written there, we refer to those as half equations. So these are the half equation. This is the half equation for oxidation process. This is the half equation for the reduction process. Oxygen is a diatom, So I can write it like that. So let's see the overall reaction. So sodium loses electrons, is oxidized oxygen, gains, it needs 2 electrons, and I'm using half in order to obtain 2 minus. Half of 2 is 1, just to balance. And the 2 electrons is because oxygen is in group 6 and it requires 2 electrons. So when I'm now writing the balanced redox reaction, I must balance the electrons given should be equal to the electrons gained. So in order to balance this, I now multiply the first one by 2. So that I now have 2 sodium atoms reacting to give 2 electrons, and those 2 will now balance 1 oxygen atom. So that we now have Na, 2 of them plus half O2 will now combine to give me Na2. That's the formula now of the sodium oxide. So in this reaction, the sodium has been oxidized because here it is a plus. Oxygen has been reduced. Why? Because it now moves, moving. It has gained 2 electrons, so it's now being reduced. That's the definitions in terms of electrons. And this is also how you now come up with redox equations. You first write the half equations, the oxidation half equation, then the reduction half equation, and in each equation you balance the atoms as well as the charges, and then you join the 2 half equations. When you are joining the 2 half equations, you must make sure that you balance the electrons produced should be equal to the electrons gained. Let's now move on to the last definition, oxidation, in terms of oxidation number. But before we define in terms of oxidation number, let's first define what oxidation number means. When we look at the term oxidation number, we are simply looking at the number of electrons a particular atom, 1 mole of an atom, is going to gain, lose, or share during bond formation. Okay, so that's what the oxidation number means. Or in simple terms, we are simply looking at the number of electrons 1 atom or 1 mole of an atom of any element gains control over or loses control over during bonding. And here we are assuming that the bonding is electrovalent or the bonding is ionic. So there are a few rules which we need to know in order to calculate the oxidation numbers, and after calculating the oxidation numbers, we will then be able to deduce if reduction or oxidation has occurred. So the rules for assigning oxidation numbers. All elements, if they are on the periodic table or when they are not combined with any other element, there's an oxidation number of 0. Elements in their, or atoms in their elemental state, an oxidation number. There's an oxidation number of 0 because they've not yet gained or lost control of electrons. So they have an oxidation number of 0. Then, so examples The elements magnesium, oxygen, chlorine, hydrogen, these are diatoms. So still they are in their elemental state because they have not yet combined with any other element. So all those they have an oxidation number 0, assigning 0 to that. Then the second rule is all ions have an oxidation number equal to the charge. Equal to the charge. Three, for neutral compounds, the sum of the oxidation numbers, numbers of the atoms present in the formula of the atoms or elements present in the formula is equal to 0. We are going to work a few examples to demonstrate this. Then for all metals, group 1, 2, 3 elements have an oxidation number equal to the charge. Metals have oxidation number equal to group number, because the group number is the charge they are going to attain after losing electrons. So e.g. sodium, when it reacts, it's going to form an ion of +1. Why? Because it's going to lose 1 electron. The one in group 2, we have a charge of +2, because it's going to lose 2 electrons during bonding. Then oxygen has an oxidation number of -2 in all compounds, with the exception, please take note of the exception, except when it is in peroxides, e.g. hydrogen peroxide. The oxidation number of oxygen in the peroxides is -1. Then the second exception, when it is bonded to fluorine. Fluorine is more electronegative. That is, fluorine is a greater desire for electrons. As a result, when fluorine is directly bonded to oxygen, then it means the 2 electrons which are being shared, the electron cloud will be shifted more to the chlorine side, because it is the one that has a greater pull for electrons. Hence, oxygen will have an electron deficiency. And to show that it is electron deficient, then in fluorides, when it is bonded to fluorine, oxygen has an oxidation state of +1 or +2. It will have an oxidation state of +2. Generally, it will just be positive. +1, +2, whatever, but it will be a positive oxidation number. Okay. Then hydrogen the other one now 6. Hydrogen has an oxidation number of +1 in all its compounds except, let's again look at the exception, except, so in all compounds where we have hydrogen, its oxidation number, we assign it +1. But when is this going to differ? This is going to be different when it is bonded to a metal, except when bonded to a metal. In this case, a metal is the one that has a greater desire to give electrons compared to hydrogen. And in this case, we say the metal is more electropositive. Hence, hydrogen has no choice. It must accept the electrons which are being given by the metal. Hence, hydrogen will have a negative oxidation number. So, when it is bonded to a metal, hydrogen is an oxidation number of -1. When it is bonded to a metal, hydrogen is an oxidation number of -1. For example, in the metal hydrides. Magnesium hydride, for example. Magnesium is an oxidation of +2. Hence, hydrogen, each hydrogen is -1, so that they will be able to gain the electrons which are being given by the magnesium. Then the halogens, the group 7 elements, mostly even group 6 elements, their oxidation numbers, and the group 5 element, their oxidation numbers will vary from 8 minus group number, 8 minus the group number, 2 plus the number of electrons in the outer shell, up to number of electrons in outer shell. So for example, an element in group 5 is now going to pick the group number, which is 5 minus 8. So the oxidation states will vary from -3 up to +5 because it's in group 5. They will vary. So it now depends with the compound to which the element is incorporated in. So their oxidation states are going to vary. So these are some of the rules. So before we define oxidation reduction in terms of oxidation number, let's try to work out the oxidation states of a few compounds so that we can get a grip of it. Before we look at examples of calculating oxidation numbers, please subscribe to this, our new channel, Chem is Try, like it, and also click the bell so that you'll be notified whenever I post new videos on this channel. So, calculating oxidation numbers. This is what we are going to do now. Calculating oxidation number. So for example, I want you to determine the oxidation number of sulfur in sulfuric acid. Let's determine the oxidation number of sulfur in sulfuric acid. So the working that we are going to do is, first we are going to assign any letter of the alphabet to represent the oxidation number of sulfur. So let oxidation number of sulfur be, I like X. Okay, so let it be X. And this is a neutral compound because there is no charge. Hence, and here hydrogen, there is no metal. So the oxidation state of hydrogen is +1. And I have 2 of them. So I have 2 times +1 plus X. Plus, I have 4 oxygens, and this is definitely not a peroxide, and it's definitely not bonded to hydrogen. Therefore, the oxidation state of oxygen is -2, but I have 4 of them, so 4 times -2. And all this should add up to give me 0. So we now end up with an algebraic expression, and we now need to solve that algebraic expression. So it's +2 plus X minus 8 is equals to 0. So let's compute this. X is now going to be equals to +6. So the oxidation state of sulfur in sulfuric acid is +6. Okay, let's look at another one. Oxidation state, calculate So this was our first one. The second one, let's calculate the oxidation state of nitrogen in NH4 plus. It's an ion. For ions, the sum of the oxidation states should add up to the charge. So again, nitrogen, let it be X, like X. So it's X plus 4 times plus 1. And this should be equals to plus 1. If there is no coefficient up there, it simply means it's a single positive charge. So again, X plus 4 is equals to plus 1. So let's make X the subject of the formula. I subtract 4, so it becomes minus 3. So the oxidation state of nitrogen in the ammonium ion is minus 3. Basically, that's how we calculate the different oxidation states. So let's now look at a redox reaction so that at the end we'll be able to say who is oxidized and who is reduced. This is a decomposition reaction. This is a decomposition reaction. But let's see if there is any redox in it. What is the oxidation state of nitrogen in the ammonia? So the oxidation state of nitrogen in the ammonia is X plus 3 plus 1. It should be equals to 0. So that X at the end is going to be minus 3. And here, the oxidation state of hydrogen is plus 1. Because it's bonded to a nitrogen, so it's plus 1. So nitrogen is equals to minus 1 in the ammonia, and hydrogen is equals to plus 1 in the ammonia. Now, let's see what they've changed into by considering the oxidation states of the products. Entity, all the elements in the elemental state have an oxidation state of 0. So hydrogen is in its elemental state, so it's 0. Nitrogen is in its elemental state, therefore it is 0. So for hydrogen, we are moving from plus 1 going to 0. Is the oxidation number, is that number increasing or decreasing? Let's look at a number line. 0, 1, 2, 3, 4. Plus 1. 1, 2, 3, 4. Going this side is positive. Then going this side is negative. So minus 1, minus 2, minus 3. So we are starting from plus 1 and we are going to 0. Therefore, we are going backwards. So we are decreasing. Isn't it? So hydrogen in the ammonia is reduced because practically a decrease in oxidation number. So reduction is decrease in oxidation number. In our example, hydrogen in ammonia is reduced since oxidation number is being reduced, since the oxidation number is decreasing, or the oxidation number decreases or decreased from plus 1 to 0. That was a decrease. Then nitrogen, it was at minus -3 and it moved to 0. So what has happened? Are we increasing? We are moving in the positive direction. Hence we are increasing. So for nitrogen in ammonia, the nitrogen in ammonia is oxidized. It is oxidized. Okay. because the oxidation number increased. Oxidation number increased from -3 to 0. The oxidation number increased from -3 to 0. Therefore, it is oxidized. So oxidation is an increase. Oxidation is an increase in the oxidation number or oxidation state. So this is how you simply tackle these simple questions. But at the end of the day, we say chemistry is difficult. Chemistry is not difficult at all. It is you who does not want to try. Chem is try. So you work out the oxidation states of the elements or the compounds in the reactant side. Then you compare with the same elements in the product side and see what would have happened to the oxidation state. Has it increased or has it decreased? So basically, this is how we define, and this is also how we obtain our justification. Whenever you're asked to explain why you are saying oxidation is okay, it's easier to calculate the oxidation numbers, and you can say, oh, the oxidation number has increased, therefore oxidation. So it has been oxidized, or the oxidation number, there's a decrease, therefore there's reduction. Okay. The last two terms I want to define before we call it a day is an oxidizing agent and a reducing agent. What is an oxidizing agent? And what is a reducing agent? Okay, my side hustle is I market different varieties of Colgate for a particular company. So I'm an agent for that particular company, promoting the brand of Colgate which they make or which they sell. So what am I exactly? If I'm marketing a particular Colgate brand as an agent, does that make me the Colgate? No, I'm simply facilitating for the increased sale for the particular Colgate brand. So if I'm saying it's an oxidizing agent, what does the oxidizing agent do? It simply facilitates the process of oxidation, because it's an oxidizing agent. It facilitates oxidation. In order to facilitate oxidation, let's give a very simple example. I want to be known as someone who gives. But for me to be known as someone who gives, I need agents. What type of agents do I need? I need people who must receive the things that I give, so that I'll end up being known as a very good and cheerful giver. But I cannot be known as a good and cheerful giver if there are no individuals to receive what I have to give. So the people who receive what I give are the ones who are the agents, who give me that, that name or that popularity, so to speak. Okay, so an oxidizing agent is a substance that facilitates oxidation, and oxidation, we said, is loss of electrons. So for there to be loss of electrons, it means there should be someone who receives the electrons. So at the end of the day, in simple terms, an oxidizing agent is an electron acceptor. As the substance accepts the electrons, it undergoes reduction. So it's an electron acceptor. Thus, it undergoes reduction. And vice versa. So a reducing agent, it facilitates a reduction. There is now I'm going to be known as someone who receives. For me to be known as someone who receives, it means there must be someone who is prepared to give. So, me who is the promoter, what must I do? Okay, so the reducing agent is an electron donor. Because for me to be known as a good receiver and a cheerful receiver too, there must be someone who is willing to give. So a reducing agent is an electron donor. Hence, it undergoes oxidation, which is the loss of electrons. So as it gives the electrons, the reducing agent, the oxidizing agent will gain. Okay? So basically, these are the definitions that we are going to also meet. So in our example there, who is the reducing agent and who is the oxidizing agent? Remember we said an oxidizing agent must undergo reduction. So who was reduced? And a reducing agent must undergo oxidation. So who was oxidized? Your answers in the comment section. So please remember to subscribe, like and share. And we notify you when we produce the next video, mostly suitable for A level. How to construct redox equations. That will be our next port of call. Thank you.